In this module, we'll cover the facade pattern. It's intended to provide a higher level interface over a subsystem to make the subsystem easier to use. I'm Kevin, and I'll guide you through this module. We'll start by describing the pattern using a real-life example. As a real-life example, which we'll also implement, we will use a discount calculator service. After having described the pattern, we will map it to a structural example. We'll continue with learning about use cases for this pattern and pattern consequences, and we'll end the module by looking into related patterns. Let's dive in. The facade pattern is a commonly used structural pattern from the well-known Gang of Four design patterns. The intent of the facade pattern is to provide a unified interface to a set of interfaces in a subsystem. It defines a higher level interface that makes the subsystem easier to use. Let's think about that by studying a real-life example. You're building a system in which you want to know the discount a customer will receive. However, calculating this can be quite complicated. First of all, we need to call into a service that checks whether the customer has enough orders. Then, we need to calculate the discount base percentage, which depends on the customer. For example, the percentage can be different depending on the country the customer is from. Lastly, a factor must be taken into account depending on the day of the week. This is something you sometimes see at airfare sites. This calculation thus isn't trivial, and it has to be done in different parts of your application. Putting a facade in front of it hides away the complexity. So it's an abstraction and encourages reuse. We could name that discount facade. It contains one method, calculate discount, which is responsible for calling into the various services and calculating the actual discount percentage. So that's our real-life example. Let's map this to the pattern structure. The structure of the facade pattern is pretty straightforward. First of all, we have a facade that maps to our discount facade. This facade has knowledge about the subsystem classes that are responsible for a request, and it delegates requests to the appropriate subsystem classes. That subsystem that are all our other services or classes. The order service, customer discount service, day of the week's factor service, and more are all subsystems. They implement their own functionality as needed, and they handle the work assigned by the facade object. In other words, methods called by the facade are implemented in a subsystem. The subsystems themselves don't have knowledge of the facade. Let's implement our real-life facade example. The first thing we want to do in this demo is creating the subsystem classes. Our first subsystem class is an order service. It should check whether the customer has ordered enough in the past to be eligible for a discount. It has one method, has enough orders, which accepts a customer ID. We do a fake calculation here for demo purposes. Any customer with an ID larger than 5 is assumed to have made enough orders. The second subsystem class is the customer discount base service, which is used to calculate the discount percentage base. These calculations can be quite extensive. You could take the country into account, you could take the amount of orders or total order price into account, and so on. We'll fake this too for demo purposes. If the ID of the customer is larger than 8, he or she gets a 10% discount, otherwise a 20% discount. The last subsystem class is the day of the week factor service. We use a switch statement on the day of the week, stating that during the weekend the factor is 0.8 and otherwise it's 1.2, which means orders done during the weekend get discounted less, while orders done on other days get discounted more. So these are our helper classes. On to the facade itself. We'll name it discount facade. It's a new class which should contain references to our subsystems. So we add 3 references to the subsystems. We could inject these instances via constructor injection, but in our case we don't have an IOC container set up, so this time we'll just new them up. We could also add the constructor anyway and let the client class provide us with the subsystem class instances. Then we need to calculate the discount. We add one public method, calculate discount percentage, which accepts a customer ID. First we call into the order service. If the customer doesn't have enough orders, we return 0 as the discount percentage. Otherwise, we multiply the discount base with the day of the week factor and return that value. And that's it for the facade. Our pattern is already done. Let's test this. We new up a facade object. For that, we need to add a using statement to facade. And then we test our facade by trying to get a discount for customer with ID 1 and one for customer with ID 10. Let's give that a try. And there we go. No discount for the customer with ID 1 because the ID of this customer isn't larger than 5. Customer with ID 10, on the other hand, does get a discount. That's it for this very simple pattern. Let's check out the use cases for it. A first use case for this pattern is obviously when you want to provide a simple interface into a complex subsystem consisting of a bunch of subsystem classes. In that case, when the subsystem becomes more complex, this has no effect on clients using the facade. It's also useful to consider this pattern when there are many dependencies between a client and the implementation classes of the abstraction. By putting a facade in between, you decouple the subsystem from the clients. Let's have a look at the pattern consequences. There's 3 main consequences to this pattern. First of all, it shields clients from subsystems. That means that the number of objects that clients have to deal with are reduced. It also promotes weak coupling between the subsystem and its clients. The client is coupled to the facade, not to the subsystems per se. Thanks to that weak coupling, the subsystem components can vary without affecting the client. That's the open-closed principle from the solid coding principles at work. And lastly, even though it shields clients from subsystems, clients are not forbidden to use the subsystem classes if they want to. Let's cover the related patterns next. From the creational family, there's the abstract factory pattern that this one is related to. It can be used together with a facade to provide an interface for creating subsystem objects while remaining independent of the subsystem. Abstract factory can also be used as an alternative to facade to hide platform-specific classes. Up next, from the behavioral family, the mediator pattern. Like facade, it abstracts functionality of existing classes, the subsystems in our example. But it's not the same. The purpose of the mediator is abstracting communication between objects, often centralizing functionality that doesn't belong in those objects. Facade, on the other hand, simply abstracts the interface to the subsystem objects to promote ease of use. It's also related to the adapter pattern. With adapter, you're making an existing interface usable by wrapping one object. With the facade, you're defining a new interface for an entire subsystem of objects. And with that, it's time for the module summary. The facade pattern is a very common pattern that makes it easier for a client to use subsystems by providing one or more interfaces into those subsystems. It's essentially a higher level layer to make the subsystem classes easier to use. Up next, another pattern from the structural pattern family, the proxy pattern.